Before I start and tell you what millimeter wave technology, let me give you a brief introduction why even we are excited about this technology. If you look at some of the today's emerging applications, unfortunately existing wireless infrastructure cannot support. So let me tell you a few of these applications. So for example, when you look at the virtual reality application, so virtual reality headsets today they require a cable connection, which significantly limits the user's mobility. And the reason is because these applications require 7 gigabits per second wireless link to transfer the data from the PC to the headset. And today's wireless network, they cannot support such high data. Another application is autonomous cars. Intel has predicted that future autonomous cars are going to generate 4 terabytes of data per day. So this is a huge amount of data, which means there is going to be a humongous amount of data which needs to be sent to the cloud from the car using wireless. And I'm sure most of you have heard about 5G, which is promising to enable 1,000 times higher speed than 4G. So unfortunately, today's wireless network and traditional wireless network cannot support such a high data rate that emerging applications require. And yes, no, definitely. I would like that. Yes, yes, yes. No, that's what it's predicted is per car. This it this is the, but so let me emphasize that this is the generated per car, but not all of these data needs to be sent to the cloud. But this is the per car generated data. It's per day. Yes, yes. It will be actually. Yes, but keep in mind, yes, but you should not divide it by 24 hours because the car is not driving on the highway or the road 24 hours. So let's say each car, I don't know, it's 5 hours on the road. So if you divide it, still it's going to be a huge. Yes. So these are camera data, it's LiDAR data, it's radar data, and some local information about the sensor of the car. But vision-based data, it requires lots of, yes, yes, sure, yes. So I think AV can support 7 gigabits per second, which is based on millimeter wave. I think so. The issue is that for VR, you need these 7 gigabits per second all the time. Even if your today Wi-Fi it can hit a gigabit per second, it cannot simultaneously support you for that. It seems to was almost yes, because it echoes that. Okay. So that's basically motivation why even people have started looking at the millimeter wave technology. Now let me tell you what millimeter wave technology and why potentially it can solve the challenges we are facing in today's application. So millimeter wave technology refers to very high frequency signals. In fact, if you look at the spectrum that we are using today, here is what Wi-Fi and LTE is operating today, and here is the band that millimeter wave technology is offering here. So not only the frequency is high, but also they have a huge amount of bandwidth available. And this is nice because, as we know, when the amount of bandwidth increases, the amount of data rate also is increased. So by using this technology, I can enable very high throughput wireless links, and then use this technology to enable all those applications that I initially talked about. So now the question here is, what's the difference between millimeter wave technology and today's wireless network? Why is it challenging to design wireless network for millimeter wave technology? So let me tell you what's the fundamental difference between millimeter wave technology and today's wireless network. So if you look at today's wireless network, either it's LTE or Wi-Fi, what's nice about them, when the access point wants to communicate to the user, they transmit their signal in an omnidirectional fashion. Now this is very nice because when the user moves, still it can hear the signal from the access. And this makes it very nice and very simple to design wireless network for lower frequencies such as today's Wi-Fi and LTE. But unfortunately for millimeter wave technology, it's not that simple anymore. So because remember, I told you millimeter wave technology works at very high frequency signal. And when you go to at that high frequency signal, the signal attenuates really quickly. Because when the frequency goes higher, the attenuation is also going higher. So the millimeter wave devices, to compensate for that loss, what they do, they focus their energy inside of a narrow beam. Now, if the access point wants to communicate to a user, so they need to align these beams, and then they can communicate to each other. Now, this is creating lots of challenges, because when you have two of these devices wants to communicate to each other, first they have to create these beams, and the second they need to align them. And that's not the only problem. The other problem is that when the device moves, again, they need to realign them. So it's not as simple as traditional wireless systems that we have. Now, these kind of requirements, which you need to create a narrow beam to focus their energy to be able to communicate, it's creating multiple challenges, which through these talks I'm going to explain each of them and say which kind of work is done in our community. So the first one is beam alignment. Remember, I told you that when the access point wants to communicate to a user, they need to create a narrow beam, and then they need to align their beam to be able to communicate. The second problem is blockage. So these beams, it's like a laser beam, yeah? So any obstacle which comes in front of the beam, it can block the signal, and it can significantly impact the signal-to-noise ratio and the performance of the beam. And the third one is the hardware. We need completely new type of hardware, because these devices, first of all, they work at very high frequency signal, and second, they require to create these narrow beam, a steer the beam, which needs completely new type of hardware for creating this type of beam and also a steer. So let us start with the beam alignment requirement and see how we can solve that challenge. So, but before I tell you how we can steer and do these beam alignments, let's see how today's wireless devices, they create these narrow beams. So today's wireless millimeter wave devices, they use a component which is called phase array. So phase array is the array of antennas where each antenna is connected to a component which is called phase shifter, and the output of phase shifters are combined and it's connected to your transmitter or receiver. So when we use multiple antennas and we create an antenna array, so instead of transmitting omnidirectional, now we can create a narrow beam and focus our energy. And by using these phase shifters, we can adjust the phase of each antenna. And by doing that, not only we can create a narrow beam, also we can steer this beam electrons. And this is exactly how today's millimeter wave devices, they create a narrow beam and also steer it electrons. They use the antenna array, where each antenna is connected to a phase shifter, and the output is combined and connected to a transmitter. Now that we know how we can create these narrow beam and also steer it, so let's see how today's wireless devices, they do the beam alignment. So actually before that, so let me tell you what should be the value of these phase shifter to do that, creating the narrow beam. So if we go and look at the antenna array literature, what's interesting, antenna array is exactly the same as Fourier transform, except that instead of having the time domain, now we have the signal that we are receiving at each antenna. So basically in this equation, f prime is the inverse Fourier matrix, x is the signal that I'm receiving from different directions, and h is the signal I'm receiving at different antennas. Now, if you go ahead and write the power that you are receiving at the output of the phase array, it gives you this equation. But all this equation tells you that if you want to create a narrow beam, what we should do is to set the value of the phase shifter to one row of the FFT matrix. Now, if I want to create another beam toward another direction, all I need to do is to set the value of phase shifter to another row of FFT matrix. And this is exactly how you can use the phase array, which is the array of antennas, and steer the beam to different directions. Now, let's see how today's wireless device, they do the beam alignment process. Remember, again, I said that when the AP wants to communicate to a client, they need to align their beams first, and then they can communicate. So the simplest yes. Yes. How many wide? It really depends to how many antennas are using. The beam width is a function of how many antennas are using in your array. But typically we are talking about maybe 10 degrees. 10 degrees is when you are using around maybe 10 antenna in each dimension. So, yeah. Phase array. So I think in terms of phase array, so you probably know better than me what's in market in the phase array. I think IBM has 64 elements. 64. IBM has 64 elements. I think some of the access points which are in the market right now, they have 8 elements, if I don't make a mistake. It's not big mistake. Sorry? 32, which one? Oh, okay. So they have 32, but this is typically what you see in the market. It's around 32, 64, it's that number. So the cost, I don't know if it's commercialized yet. It's not. I don't know if that one is commercialized. How much is it? Yes. Yeah. So I personally built one with 8 elements, and so the cost mostly was phase shifters was a bit expensive, and I think with 8 elements cost around I think its phase shifter was around $60, like $500 it cost us this one. But I don't know what's the challenge right now, but when I built it, phase shifters was the most expensive part. The PCB, the rest wasn't that much. The range, it really depends how many elements you are having, how much power you are transmitting. So with 8 elements at 100 meters, I was getting SNR of around 16 dB, 15 dB. That and also it really depends which frequency you are operating. I was operating at 24 gigahertz, so which is better in terms of range than 60 gigahertz. It was it yes. If you calculate the wavelength, it's really not millimeter wave; it's on the range. But in terms of all properties, it is millimeter wave. You really need to have a phase array. Everything is the same. You need to do beam alignment. And in fact, many companies are focusing on 24 gigahertz because there is the ISM bandwidth. And components are also cheaper and more available than 60 gigahertz. Any other questions? So the simplest one is the exhaustive search. So in this type of search, when the AP wants to communicate to a client, each of them, they create a narrow beam, and the AP is trying n possible directions, while the client also is trying n directions. So as you can see, this process is extremely slow because you need to try n squared measurement. So you need to try n squared direction. And imagine these beams can be as narrow as 10 degrees or even narrower. If you want to scan the whole 3D space, it can take a huge amount of time. And that's exactly why people in the community, they have started looking to see how they can make this process much faster, how you can make the beam alignment process faster. And 802.11 AD scan is proposed, which in this scan, instead of having both AP and client to create a narrow beam and scan the whole space, the AP is creating a narrow beam, while the client is trying to create a quasi-omnidirectional pattern. So client is an omnidirectional pattern, while the AP is scanning the whole space to find the direction of the client. So when the AP finds the direction of the client, then they switch. The AP is transiting in a quasi-omnidirectional pattern, while the client is scanning the whole space to find the direction of the AP. So this process is much faster than exhaustive search because you only require the big number of measurements is n. You need n measurements or n directions to start. But still, for some mobile application, it is slow. And the second problem that this approach has, because at any moment one user is transiting in a quasi-omnidirectional pattern, you lose the range. Because remember, the whole purpose of creating a narrow beam was to achieve higher range and also achieve higher estimate. Yes. So I think they are using it for receivers. They are using it. And this is exactly why there are some follow-up work to see how you can increase this beam alignment process. So there are so many works. So what I'm going to briefly talk about two of them. So the first one is based on the type of the work, which is doing some training at the beginning. So basically at the beginning, you spend some time and scan the whole space to find the best beam alignment direction, and also second and third. So whenever the blockage is happening in the first one, now you know what's the second one and third one. So basically you can choose based on that. And the idea is that, let's say I have a transmitter and I have a receiver. This was the best direction for beam alignment. But when I scanned also, I found the other path which used the reflector. Now when the main path is getting blocked, I can easily switch to the second path without scanning the skin. Yes, I do. I do. Another type of work is what is published in sitcom. So instead of creating a narrow beam and scan the whole space, what they do, they create a multi-arm beam. So let me tell you what they do exactly. So the best way to explain this is with an example. So let's say there is a client and there is the AP. And the client is at 60 degrees with respect to the AP, and the AP is trying to find the direction of the client. So instead of creating a narrow beam and scan the whole space, they create a multi-arm. So let's say client is transiting and AP can hear the client. What does that mean? That means that the client is at one of those directions, agree? I don't know exactly which direction, but because AP can hear the client, it means the client is at one of those directions. Yes. Yes. No. No. Yes. Yes, exactly. So the range is going to be reduced here because if you think of transmitter, it's the same as receiver. Let's think about transmitter. Instead of sending all the power in one beam, now I'm sending it in 4 beams. But the hope here is that you can do these training at a lower data rate, at a lower SNR, find the direction of the user, and then focus all of these beams to the same direction and achieve high data. Exactly. So I know that the client is at one of those directions, but I don't know exactly which one. So what they do, they try another multi-RB. Again, the client is transiting and AP is listening to the media, and it knows that the client is at one of those directions. It's not clear which one, but it's one of those directions. Now what's interesting here, if you look at the possible direction, only 60 degrees come in between. And this is exactly how Agile Link can find the direction of clients with respect to the edge. So going back to how to create these multi-arm beams, you mentioned that we lose the range, but let's see also how we can create these multi-arm. So remember, I already said that when you want to create a narrow beam toward one direction, you set the value of the phase shifter to one row of the FFT matrix. Now, if you want to create a multi-arm beam, what you do, you divide the value of phase shifter to segments, and you set each segment to the corresponding segment, but from different row of the FFT matrix. So I choose different row of FFT matrix, and you put it to the phase shifter value, and that's how they generate the multi. If you want to generate another multi-arm beam, you do the same thing. Again, you divide the value of phase shifter to segments, set each segment to the corresponding segment in the FFT matrix, but from different row of the. So this is simplified version in 1D, but you can extend it to the 2D. It's gonna be exactly the same. In real life, it's 3D because your beam it really depends to the application, but ideally you want to have a 2D array where you can, narrow your beam in 2 dimensions. It becomes n squared. Well, if I have 4 elements in one array versus 4 by 4, 16, so hardware becomes more, everything, computation also is the same. It's all of them. Yeah. I will get to the hardware thing, yes. But also the hardware, so going back to the power consumption, it depends also how many chain you are using. You might use antenna array of 64 elements with a single chain. Although you need maybe LNA per each antenna, but you don't need a full chain per each antenna. You have one full chain. Yes. So you consider side lobe. So basically, so what's happening here, they use a soft voting mechanism. Sorry? Yes. So they consider the side lobe because it's using the soft vote mechanism. So still because what they do, they give votes. They give votes to the directions that they have power. Now, if you have a slightly power because of the side lobe, still it gets votes, but not as much as the main lobe. I think the next slide probably is explaining better. Exactly. So what all this work is doing basically is hashing the directions to beams. So here you are hashing 4 directions to one beam. If there is energy inside of this beam, which means AP could hear the client, and which means the client is at one of these directions. So if there is an energy, they go back and give vote to all of those directions. But they give weighted vote, which means if it's the main lobe, it gives a full vote, but if it's a side lobe, it gives a smaller vote. And all mechanism to see which direction has highest number of votes. So the direction that has highest number of votes is correspond to the right direction of the client which plays today. So here I just gave you 2 examples of the so many works to see how they can increase these. Each of them, they have their own limitation. Of course, some of them, they lose range. Some of them, it requires training, etc. But still, there are lots of interesting problems also for beam alignment. Here, I talk about physical layer. At the MAC layer, what's going to happen, etc. The other problem I would like, yes, 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 for one, yeah. Sure. It really depends to the size of the antenna. But I can give you an example. I think in the Agile Link paper there is a table that it shows that if you use exhaustive search with around 100. Yes. Exactly. So I think there is a paper which I will briefly talk tomorrow or the day after tomorrow, that they use light to find the. So there are other works also. They use Wi-Fi, 2.4 to find the. The problem is that they can help you to find the location of the user, but doesn't mean that direction is the best for the beam alignment. So let's say I have an access point here sitting and it wants to communicate to the user on your table. So I know your direction, but if the line of sight path is blocked, knowing your location doesn't help me, because if line of sight path is blocked, I have to find a reflector on the wall and use that reflector to send signal to you. So knowing your direction is not going to help that much. What do you mean by short? No. I think, yes. For VR, yes. For VR, you are talking about 5-6 meters. No, actually, I will show the blockage problem. Even for VR, when you are playing a game, if my headset is here and the access point is there, I can easily block the signal by doing it. I will show you in the blockage what's going to happen. So now let's look at the problem of blockage, because remember, this technology is using narrow beam to communicate, so it can easily be blocked by an optical. So one application people have looked at millimeter wave was for data centers, when you can put millimeter wave access point on top of each rack, and then you can use the links to communicate between them. But the problem is that one link can be easily blocked by the second, by another rack. And the way they address this challenge in this paper is by using a mirror on the roof. So basically you can think of it as a fixed metal sheet sitting on the roof. So whenever the access point A wants to communicate to C, basically they use the reflector on the roof to communicate. So it's a nice idea, but if you look at this, it's very costly to put, a full metal sheet on a roof. So it might be possible to do it in a data center. But going back to the virtual reality application that you mentioned, I cannot put a metal sheet in my home for the whole room. So, yes. Yes. No, so this is happening already. So what's happening, you start with a narrow beam, but the beam as you go, it's getting wider, it's not, it's 10 degrees. So as you, exactly, depending on the distance, it gets wider. So basically, they are showing some results. So here is the data rate, and here is our different blockage scenario. And this is when there is no blockage. So basically, when there is no blockage, they can achieve around 7 gigabit per second wireless. Now let's see what's going to happen when blockage is happening. What's going to happen, for example, when the user moves his hand in front of the line of sight path. And here are the results. As you can see, when the blockage is happening, significantly impact on the data rate that they are achieving. Yes. Yes, the hand is staying there for some. 1 millisecond is not an issue, because the virtual reality headset is updating at 90 hertz, the display, which means every 10 milliseconds they are updating. So if the blockage is 1 millisecond, no issue. But if the blockage is 10 milliseconds, that's the issue, which most of the times are more than tens of milliseconds. Configurable mirror, it's a small device that you can put it on the wall. So whenever the blockage is happening, the access point can use this mirror to reflect the signal to the user. Now this is challenging because compare it with the data center application. In data center application, nobody moves. Everything is fixed. So if I know my location and if I know the user location, I can just use the reflector to reflect it. But here, the user is moving in the room. So the mirror needs to be configurable to adjust the beam direction toward the headset. So, yes, so the reason is that if you put it in the roof, first of all, there is a problem. The deployment is not going to be easy.
But the main problem is that even if you put it in a roof and you are playing a game and you put your hand here, still it. Because remember, in virtual reality play, when you play a game, you put this headset and you are just moving your hand. You don't know where is your hand because you don't see outside board. So there is a chance that you still block the signal if you raise your hand on top of your head. So if you have multiple access points, and I think there is a paper, again, tomorrow or the day after tomorrow in this Mobicom, that they show how to synchronize multiple access points to communicate to the single user. The only problem is that you need to put multiple access points in a room, which are costly, the radios are costly, the hardware is costly, and then you need synchronization between them. So one challenge in virtual reality is latency, because everything needs to be real time in virtual reality. Remember, I have 10 milliseconds to get the data from the PC to the headset. So if I cannot pass that latency, then it's going to cause a problem in the display. So by using these configurable mirror, they can basically, whenever the blockage is happening, they can use the mirror to send the data to the mirror. And the mirror is not a full chain hardware. It's just two phased array and an amplifier between them. So it's receiving the signal from one phased array, amplify it, and send it to the second phased array to send it to the user. There is a chance. Yes, definitely. If there is a possibility to do that, but you can put more than one mirror in the room. Not, sorry? Well, of course, it's going to add up, yes. But the difference is that these mirrors only need power. So it's different from access point. If I put a full access point, you need to cable that full access point to the PC. But these mirrors are only require a power, which can be powered up with a battery. Yes. In the access point or the mirror? Yes, the mirror, so you need, exactly, you need the AGC to control the gain of the amplifier. What they do, they monitor the power consumption of the amplifier, and whenever it goes to saturation mode, they bring the gain down, basically. Yes, yes, yes. Yes, yes. Because all you get is from side lobes. So by choosing a right location for that, these are two separate devices. They are two-phase array like this. You can put it, and they are amplifier between them. But still, there is some self-interference which causes the amplifier to go to saturation mode. By controlling the gain, you can bring it below the saturation. Yes, it's happening. If you put so much gain, it's happening. But these side lobes are typically around 15 dB lower than the main lobe. So 15 dB in the transmitter, 15 dB in the transmitter, you already have 30 dB attenuation between your antenna compared to the main lobe.
Yes, but there's a huge difference. So the set interference
Yes.
from what you are saying
Yes.
is previous topic.
Yeah.
So the access point, access point to the mirror.
Yes.
Let's say the distance is 5 meters.
Yes.
Whereas these two things are
Yes.
a few centimeters.
Yes. Yes.
The difference in propagation loss between these two is huge.
Sure, but I'm saying the signal that the mirror is receiving and then it's transmitting, some part of it, it's here back by itself. And that's the issue you are raising. But the lobe that it's hearing this signal, it's 15 dB to 20 dB lower than the main lobe that it's hearing this signal. And this is just 3-4 meters, yeah? It's not like hundreds of meters.
The point I'm trying to make is the mirror has to transmit to the VRA.
Yes, it has to.
5 meters away.
Yes, that's
It
true.
has to put out enough power.
Yes, that's
Whereas this receiver
yes.
is receiving from a few centimeters away, the same amount of power.
Yes, it's not the same power. It's not the same power.
The power
You have a lobe. You have a main lobe. You have a main lobe here. So it's receiving from the side lobe, not the main lobe.
difference in
it's around 15, 20 dB. Because it's not the largest side lobe. It's the side lobe exactly 180 degrees. Yeah, you have two. Yeah, yeah.
I'm getting at is if you have let's say 15 centimeters,
Yes.
Versus 5 centimeters difference versus 5 meters.
Yes.
One side.
Yes.
That's a fraction of 10. Right? No, 100. 5 centimeters to 5 meters
Yes.
is a ratio of 100.
Yes.
20 log 100.
20 log 100.
That's what I'm getting at.
So it's 20 dB.
40 dB.
No, it's 10 log of that value.
R squared.
Yeah, R squared, then it's 10 log then.
R squared.
Yes, but I'm saying the distance was 100 times difference. So it becomes 40 dB. Yes. It's 40 dB.
So, you see 15 dB does not solve the problem. That's what I'm saying.
Yes, but there is another 15 dB also from the other side. And I think it's more than 15 dB because, again, this receiver is aligning its beam toward the antenna, yeah? But the receiver you have here, again, it has a side lobe, which is receiving. It's on that board, yeah. So now, this is another type of work that people have done basically to show how you solve the blockage problem. So either they are designing mirror or this type of repeaters, or what they do, they say basically pick another path, find another reflector and use that reflector to basically transmit the data, but there is a trade-off. If I use the reflector in the environment, they attenuate the signal significantly. While I'm using the mirror, it amplifies it, but it needs a hardware and extra cost to put. Now, I would like to also go to the hardware and mention a few challenges in designing the hardware. So, if you look at the simple architecture of a hardware, you have a phase array of antennas. Each of them is connected to a phase shifter. And then you have your transmitter or receiver chain where you have RF chain, DAC, and your digital baseband. Now, I wanted to show you how today's basically phase array look like in reality. So these are some phase array designed at, I think, 60 gigahertz and higher frequency, which have around hundreds of or more elements. This is the 8 elements I mentioned to you. So there are 8 antennas sitting there. It's a one-dimensional array where each one is connected to a LNA and also the phase shifter. And by adjusting the phase of those phase shifter, now you can adjust or steer the beam, basically. So here is what it looks like when we talk about the phase array. So the challenges in designing phase array, there are so many challenges, but a few of them I wanted to mention to you. Phase shifters are not exactly, when you tell them put the signal phase at 20 degrees, they have some error. So they require calibration. Basically, you need to do calibration for phase shifters. Otherwise, the beams that you are creating, they're going to have a large side lobes. Another challenge is that when you get very large phased array, how do you get the signal to each antenna? So the dimensions are so small because the wavelength is high. The antennas are so small and they are packed to each other that bringing a signal to all antennas is very challenging. And the last one is the fabrication. Again, going back to the frequency, because the frequency is very high, so fabricating this PCB or this hardware is not the same as traditional hardware. It requires completely new approach to fabricate them. Yes? Yeah. Nano scale? Yes. I'm not sure exactly. I don't know if you. I'm not sure exactly. You mean send the data wirelessly to them? But then you need a whole receiver to sitting below each antenna, no? Yeah. Sorry, I don't know if you are familiar. Yeah. So now that we look at the phased array, There are so many challenges also on building the RF part. So here are a few hardware that has been built in Mobicom and also available hardware commercially available. This is Pasternak hardware. Somebody was asking about the cost. I think each of them costs around $10,000 or more. And these are two different hardware which has been presented at Mobicom, OpenMelee and Mira. So OpenMelee has a phased array working at 60 gigahertz, and also it has the full chain basically, but it's more costly than Mira. Mira works as a front end for USRPs. So basically it's connected to the USRP and they use USRP as baseband processor, and it works at 24 gigahertz. So some of the challenges that we are facing for the hardware, especially at the digital baseband. So remember, millimeter wave frequency, they want to use a huge bandwidth. In fact, if you look at 802.11 or 60 gigahertz, each channel is 2 gigahertz of bandwidth. So the baseband processor needs to process lots of data. And unfortunately, the baseband processors that are available today for such a high data rate either are so much expensive or they have very high power consumption. So even the ones that they use USRPs, they can only support around 160, 200 megahertz of bandwidth simultaneously. So it's very challenging to design a baseband processor which can support 7 gigabit per second of data. Another challenge at those frequencies is noise, especially carrier frequency offsets. You know, in reality, when we have a transmitter and receiver, there is an offset between the frequency of receiver and transmitter. And when you transmit Wi-Fi packets, you use some training to find the offset and then basically fix it. But as the frequency goes higher, this frequency offset gets bigger and bigger. And it's very hard to correct the frequency offset when you are working at 60 gigahertz to fix your Wi-Fi packets. So this can significantly impact on your SNR if you don't correct it properly. And the last one is power consumption and cost. So today's millimeter wave radio, mostly they are higher power consumption, significantly higher power consumption than traditional radios, and also they are much more costly, which I'm hoping that they can, design hardware that they are much more efficient than basically what we have today. So far I talked about millimeter wave and communications. I don't have that much time, but briefly I want to mention that there are other applications for millimeter wave, especially tracking and imaging, because the frequency is so high and the wavelength is so short, so it gives you very high resolution for tracking purposes and also imaging. So for tracking, the best well-known work probably most of you are familiar with, it's Google Solid. What they use millimeter wave technology for gesture recognition and also finger tracking. Again, going back to the resolution, because the wavelength is so short, so they can track the hand movement in millimeter. There are other works also has been done in Mobicom when they use millimeter wave technology for tracking metal objects. For example, they can track pen and pencil and basically see what the user is writing using the wireless signal. For imaging, the best example is what you have seen at the airport. When you do this and they scan your body, they use millimeter wave technology. There are also some works at Mobicom. Just to give you one example, in Mobicom 2015, there is a work that it's using a transmitter mirror, working at millimeter wave, and then they use a receiver which is moving, and it creates basically antenna array where it can scan the space to image an object. There are 4 papers at Mobicom this year. I highly encourage you to go to that session. So there is a paper Mute, which is talking about multi-stream beam training for millimeter wave. So most of the stuff I talked about is that you have a single stream between the access point and clients. But if I can do MIMO for millimeter wave, basically if we combine the MIMO and also millimeter wave, then I can transmit multi-streams from the access point to the users. And they have some nice algorithms to do beam alignment for multi-beam, basically multi-stream millimeter beam. There is another work, UBIG, which is, I already mentioned it briefly. What they do, they show how you can use multiple access points to basically be synchronized and send data to a single user. This is beneficial in the case of blockage, because if I have a single access point and it gets blocked, now I can use the second access point or third access point to transmit the data. There is ACO, which is Adaptive Codebook Optimization for 802.11ad. If you remember in 802.11ad, I briefly mentioned it at the beginning. You have an access point. It's creating a quasi-omnidirectional antenna. And then the user is using a narrow beam to scan the whole space. So what they do, they have optimized basically this codebook or these beam patterns to speed up the beam alignment process. And the last paper in that session, it's a very cool idea. What they do, they use the LED on the access point to find the direction of the access point to the users. Basically, if my cell phone has a light sensor, then it can use that light to find the direction of the access point and basically speed up the steering process. So with that, I would like to mention that millimeter wave is an amazing technology in enabling very high throughput wireless communication and also very high resolution tracking and imaging. And it's an exciting time for millimeter wave, which can potentially enable many new applications. With that, I'm ready to take more questions. Thank you. Yes. Yes. So I think there are different type of works. Some of them, they are using very narrow pulse, ultra-wideband pulses. Some of them are using FMCW. So basically, FMCW is using a sine wave and sweeping through the whole bandwidth. And then by receiving the same signal and multiplying by transmitted signal, they can find time of flight. And from time of flight, they can find the distance and then localization. So I think in terms of hardware, probably FMCW is easier to build because you have a single sine wave and you are sweeping it. But I have recently also saw some hardware in the ultra-wideband, ones. I think in the past was maybe FMCW was easier, but I have seen both approach. In terms of power consumption, honestly, I don't know which one is better. Thank you.